Hello, everybody, and welcome back. So we talked about the normal distribution and specifically the standard normal distribution. We looked at how to find areas underneath that standard normal distribution and made the important connection that since the total area is 1, we're going to use that area to model probability. And so I want to tackle a couple of new looks. I want to talk about percentiles. I want to look at how to go from an area back to a value, and then we'll look at some applications of this normal distribution. So here we go. So applying the normal distribution. So we're going to find, oops, sorry guys. So we're going to find a value that corresponds to a given area. So in the last section, we started with z-scores and found the area. But now, what I want you to notice is we're starting with a cumulative area. And again, cumulative area meaning area to the what? To the left. And so there's some z-score here. Don't really know what it is. And all of this area out here is 0.9599, okay? And so notice that this is a different situation, right? We're not starting from z-scores and finding areas. We're starting from an area and asking, okay, what z-score corresponds to that area? Well, fortunately, Excel has a nice function known as norm inverse. And so I'm going to, same thing as usual, pull up Excel here, and in my command box, I'm going to write equals, and then norm dot, and you'll see it there, the second one, norm dot inverse. Whoops, helps to actually select it. And then it wants to know the probability. You might say, wait a minute, probability, you told us area. Well, remember, area models probability. So we're going to treat that area of 0.9599 as a probability. So 0.9599. And since it's a z-score, my mean is what? 0. And my standard deviation is 1. And so that z-score turns out to be about 1.75 equals 1.75. Okay, so you've got the norm dist to find areas, you've got the norm inverse to find values that correspond to those areas. All right, so let's take a look at this next example. We have a national exam, could be an SAT, LSAT, MCAT, GRE, whatever. The mean score is a 1210, standard deviation is 225. Notice we're not talking about z-scores anymore, right? We have context. We want to know what score represents the 90th percentile. Well, what is a percentile? Well, a percentile is the percentage of the population whose value is lower than whatever we're given. So in other words, there is a z-score here, which I'm not going to call z anymore, or x for next value. I'm going to call it p for percentile with a subscript of 90. And whatever that value is, 90% of the area, or 90% of all the scores on the exam in this case, fall to the left. And so P90 is going to be, well, again, we need to find a score corresponding to an area. So norm dot inverse, and then we have a probability of 0.90. But this time what we're going to do is instead of looking at the mean and standard deviation as 0 and 1, we're going to treat it in context. The mean is 1210. The standard deviation is 225. And so let's go over here to Excel and let's see what we get. All right, so over here in Excel, we're going to go back to that norm inverse. And I'm going to type in that area, 0.9. And then again, my mean in context now, 1210 and standard deviation of 225. It's very important that you use those values because otherwise, if you use 0 and 1, it's going to be giving you a z-score. We want an actual exam score. And so what do we get? 1498, if I'm rounding, we'll call it 1498.3. 1498.3. And so again, what does this mean? What does this mean? Well, it means that 90% of the exam scores are below or less than 1498.3. Okay. All right. How about the next one? The 50th. Whoops. As I mark on my page here. The 50th. Oh, come on. Here we go. Sorry. Technical difficulties here. 50th percentile. All right. Well, let's draw this. So we've got our nice normal distribution. And 50. I'm going to come in here. I know that this area then is an area of 0.50, and I want this value right here. And so since I did the last one, I'm just going to go on autopilot here and say norm dot inverse. Oh, wait, let's not go on autopilot. Think about this for a second. 50th percentile. So what value has half the area to its left? Oh, P50, the 50th percentile, is just the mean. So P50 is 1210, okay? And if you want, there's nothing wrong with taking Excel's word for it over mine, if that's your inclination. Well, you'll get 1210. All right, and then the last one, the bottom 10%. So the bottom 10%. Well, so I've got my normal distribution here, and my area is out here in this tail. Again, it's not the top 10%, it's the bottom. So that area is 0.10. And I'm really looking for the 10th percentile. All right, well, 10th percentile. Let's come back to Excel here. We're going to go back to that norm inverse, the cumulative area or probability, 0.10, the mean, and the standard deviation. Okay, we're going to hop over to Excel. Equals norm dot inverse 0.10, 1210, and 225. And we get 921, if I'm rounding, 921.7. Okay? So there we go. Those are percentiles. All right. Let's look at some other contexts. The mean, so now we're going to look at these areas and probabilities and treat them that way as opposed to percentiles. But again, all synonymous, right? It's just what function, what modeling function are we going to use that normal curve for. So the mean fuel efficiency for a full-size SUV on the highway is 17.6 miles per gallon with a standard deviation of 4.2 miles per gallon. And you should also know that these fuel efficiencies, again, if you're not told this, or if there isn't evidence that this is the case, our analysis isn't justified. So you also need to know that fuel efficiencies are normally distributed, okay? Now, there are ways to determine if that's a reasonable assumption. Of course, it's always nice when it's given to us. So what is the fuel efficiency for a full-size SUV in the 95th percentile? In other words, what kind of mileage does an SUV get if its mileage is better than 95% of all the other full-size SUVs? So this area out here will be 0.95. Okay, and this will be P95. Well, again, we're getting used to that norm inverse deal in Excel. And so this time, my probability or my area is 0.95. My mean is 17.6, and my standard deviation is 4.2. So let's hop over to Excel and see what we get. Norm inverse 0.95, 17.6, and 4.2. I see 24.5. And let's be careful here, right? We have context, we have units, 24.5 miles per gallon, okay? All right, what percent of full-size SUVs get between 15 miles per gallon and 20 miles per gallon? Well, so here's my curve. The mean is right there in the middle. And we've got 15 here. We've got, I don't know, maybe 20 here. And this is the area that we're looking for, okay? Well, if you remember what we did last time in this situation, we can find the area left of 20, and then we can subtract the area left of 15, okay? So that's the game plan. The area left of 20 minus the area left of 15, okay? All right, so the area left of 20, right? That's going to be norm, dist, and then 20 with a mean of 15. I'm sorry, not a mean of 15. A mean of what, 17.6? And a standard deviation of 4.2. Oops. And then minus norm dist 15, 17.6, and come over to the other side here, 4.2. Okay, and so now we come over to our good friend Excel and see what we get. So norm, dist, 20, 17.6, 4.2, minus norm, dist, 15, 17.6, 4.2. Oh, and I forgot, we do want cumulative. So true and true. So we get 0.448, 0.448. Now, let's make sure we're actually answering this, right? 44.8% of full size SUVs get between 15 miles per gallon and 20 miles per gallon. All right. Next, would it be unusual for a full-size SUV to get more than 26 miles per gallon? Why or why not? Well, unusual, in other words, is the probability that we find an SUV whose mileage is greater than 26. Is this less than, well, what's our standard for deeming an event unusual? Well, probability of occurring less than 0.05, right? That's what I want to know. Well, let's sketch this out, okay? So again, right, I've got this issue, I've got 26 way out here, and I want this area to the right. So my probability that X is greater than 26 is going to be 1 minus the probability that X is less than or equal to 26, which is 1 minus, and now we go to our Excel function, norm dist, and then we have 26, 17.6, 4.2, and again, true, meaning give us all that area. All right, and we just type it in as it shows. 1 minus norm dist 26, 17.6, 4.2, and true. There we go. We get 0.023. That is less than 0.05. So this would be unusual, okay? And more specifically, unusually high. Okay? All right. So here's one that I want you guys to try on your own, simply because we've done something similar. So we have this International Journal of Contemporary Pediatrics. Go ahead and find the mean weight. We're told the mean weight of an Indian baby is 3.07 kilograms, standard deviation of 0.455 kilograms. We are assuming the birth weights are normally distributed, and I want you guys to find the 99th percentile and the 75th percentile. So go ahead and pause this and do that. I mean it. Pause it. Okay, so 99th percentile. We've got P99. This area is 0.99. How do we find data values or values along our x-axis from a given area? That's right, we use norm inverse. And so we're going to give it the probability of the area, cumulative area, 0.99. We're going to feed Excel the mean, and we're going to feed Excel the standard deviation. Okay? And before I do that, I'm going to set up the other one as well. So for the 75th, right, we have a little less area. So we should expect a smaller value. This will be P75. Well, same idea, right? We've got this cumulative area. So norm inverse, that cumulative area is 0.75. The mean is 3.07, and the standard deviation is 0.455. All right, let's compute these. And so the first one, norm inverse, let's see here, norm inverse we get about 4.128 or 4.13 kilograms. And again, that means 99% of babies born in India weigh less than 4.13 kilograms. And then for the other one, we also have norm inverse, 0.75, 3.07, and 0.455. And we get, what, 3.38, I'm rounding, so 3.38 kilograms. Okay. So hopefully you pause those and obtain those answers as well. All right. Now this one you got to be careful about. So the accelerations from 0 to 60 miles an hour of a certain sports car are normally distributed with a mean of 5.1 seconds, standard deviation of 0.24 seconds. What is the slowest a car could accelerate and still be in the top 5%? Now, before we just put this on cruise control, sorry, bad joke, and come in here and say, okay, well, top 5%, that must mean that this area up here is 0.05, and we want to find this value. But think about what this is saying. Top 5%. This really means the fastest 5%. Well, if you're talking about time, what makes something faster? What makes it faster is a smaller time, right? So just because you see top 5% in context here, that's not what we want, right? In context, when we say top 5%, we want this down here, right? Top 5% means the time is lower than 95%, right? And so this area is 0.05, and we want that value. Okay, so we want a value from a given area. So that's, again, norm inverse, 0.05. What was the mean again? Oh, 5.1. And 0.24. Let's see what we get. Norm inverse, 0.05, 5.1, and 0.24. So 4.7 seconds, okay? And we should expect that to be below the mean, right? If it's faster, we should have a lower value. It's below the mean, okay? All right, let's look at one more. Submarine, not tall person friendly. It's engineered with hallways that are 70 inches tall. Heights of men are normally distributed with a mean of 68.6 and standard deviation of 2.8 inches. What is the probability that a randomly selected male is too tall to walk through the hallway without ducking? So our notation is essentially saying, what's the probability that a randomly chosen male has a height over 70 inches? Well, what does that look like on our distribution? Well, our mean is right here in the middle, 68.6. And so 70 is over here somewhere. And we're looking for this area. Remember, this area is the probability. Area models probability. So how do we find that area? Well, remember with these greater thans, right, we're going to use the complement. I'm going to do 1 minus norm dist, and then we have the value is 70, the mean is 68.6, and the standard deviation is 2.8, and we want all the area to the left of that, so true. Okay, Here we go. Equals 1 minus norm dist 70, 68.6, 2.8, and true. So 0.309, if I'm rounding. 0.309, okay? So that means that if you were just randomly pick some male out of the population, there'd be a 0.309 chance that they would have to duck to walk through a submarine hallway. So you can think about what that does to recruitment, right? Or how you allocate human resources in the Navy. Things to consider, because this essentially says about 31% of the population is not going to have an easy time walking through those hallways. So there you go. All right, let's see here. So now you've got some looks at applying this normal distribution. You need to get comfortable using Excel. There might be some other spreadsheet options, like if you use Google Sheets or something, believe that the commands are similar. Of course, there's also calculator options, but Excel is really the go-to. For now, that's what you see me using. You know, as you're trying these problems, I would recommend you draw the distribution. Identify what region you're looking for or what region you're given, and then therefore what value along the x-axis you're looking for. You want to just organize your thoughts that way. Let the normal distribution graph and diagram, however you construct it, let that dictate your computations. Don't try to just memorize computations. Recognize that the normal distribution function in Excel is going to give you area to the left. So much like with Poisson and binomial, if we need area to the right, you're going to have to do 1 minus, okay? And just get used to that. Again, I want you to think about it from less of a memorization standpoint and more of just conforming the tool to do what you need it to do, okay? So that is the normal distribution. Next, we're going to look at a hugely important theorem, something that's going to be in use for the rest of the course. In fact, the third part of our course would be pretty light if we didn't have this next big idea. So before you get there, you want to be real solid on the normal distribution. Give yourself some practice, rewatch video, lecture, and just, you know, make things your own, okay? I look forward to next time. See you then.